University Utara, Malaysia, digital forensics is practiced as a strict, scientifically documented discipline. Every finding must be reproducible, and every action is governed by the mathematical limits of data extraction and the physical constraints of computer hardware. This side-by-side comparison illustrates the technical reality of the enhanced trope. On the left, a low-resolution image consists of a finite pixel grid. Because the camera did not record higher quality data, that information does not exist. On the right, AI restoration tools attempt to fill these gaps using statistical guesses. While the resulting image may look clear, it is a synthetic creation that lacks the evidentiary value required for a court of law. This flow diagram shows how systems secure passwords using hash functions. Unlike encryption, which is designed to be reversible, a hash is a one-way mathematical operation. An investigator cannot reverse a stored hash string back into the original plaintext password. They must instead calculate the hash of millions of guesses to find a match. Modern security protocols further complicate this by using slow algorithms like bclept and a process called salting. By injecting a unique, random string of data into the password before hashing, the system ensures that identical passwords produce entirely different outputs. This makes pre-computed lists of common hashes, or rainbow tables, ineffective. Data recovery also depends on specific hardware architecture. On an older hard disk drive, deleting a file removes the index pointer while leaving the data on the platter. However, as shown in this SSD diagram, modern solid-state drives use the trim command. This command triggers hardware-level garbage collection to actively wipe the physical memory sectors to maintain write speeds, often rendering deleted data unrecoverable. When default device encryption is enabled, the system can destroy the specific cryptographic key required to read a file or partition. Once that key is gone, the underlying data is converted into randomized static that cannot be unscrambled. These fixed properties, the resolution of a pixel array, the one-way nature of hashes, and the physical erasure of flash memory, define the boundaries of a forensic investigation. Building a verifiable case requires identifying patterns across thousands of data points. We look for correlations between system events, user behavior, and physical location to build a narrative supported by multiple independent sources. This timeline shows separate evidence tracks converging during an insider theft investigation. We align USB insertion logs, file metadata, and building badge records. Their convergence within a 5-minute window provides a high probability correlation of unauthorized access. To preserve this evidence, we must avoid any interaction that modifies the original drive. Simply booting an operating system updates log files and overwrites temporary data. A hardware write blocker ensures data flows only one way, from the original evidence to our workstation. We then generate a cryptographic hash for both drives. Matching alphanumeric strings prove our copy is an identical duplicate, establishing a sound chain of custody. Accessing mobile data involves navigating hardware-enforced security. This diagram of a smartphone secure enclave shows how the chip enforces rate limiting. By introducing mandatory time delays between failed passcode attempts, the hardware prevents external computers from rapidly testing every possible combination. Maintaining these standards requires a collaborative lab environment. Evidence custodians, imaging technicians, and analysts each play specific roles. To ensure accuracy, every finding must undergo peer review, where a second examiner verifies the methodology and the results. This structure ensures that conclusions are based on reproducible processes and a mathematically proven chain of custody rather than individual interpretation. Consider this procedural challenge. If a computer is found powered off, the protocol is to use a write blocker. But if the computer is found powered on, what is the first step an examiner must take? The examiner must perform a live acquisition of the RAM. This capture is vital because volatile memory contains encryption keys, open network sockets, and chat logs that are permanently lost as soon as the system is powered down. Forensic software suites automate the extraction of raw data and the reconstruction of file systems. The human analyst then evaluates this output to establish the context behind specific artifacts, such as determining if a browser cache image was a deliberate download or a background advertisement. We apply this same context to factory resets. While a secure wipe destroys local cryptographic keys on the device, modern computing is highly distributed. As this diagram shows, data streams are constantly syncing from the device to external cloud storage providers. An investigator shifts focus from the wiped hardware to the wider digital trail. By serving legal warrants to cloud services and internet providers, we can often recover the same messages and photos that were deleted from the physical phone. Digital forensics converts raw, fragmented data into a court-admissible narrative through rigorous preservation and mathematical verification. This summary sheet covers our core technical realities, the limitations of AI restoration, the one-way nature of hashes, and the volatility of RAM. Review these points and be prepared to discuss which one had the greatest impact on your understanding of evidence in our next UUM tutorial.